We have a very large slot for this topic, an hour and a half. I'm not sure we're going to be covering it all. I'll try and work through the slides slowly, but we may finish a little early. If this is okay with you, we can have a larger discussion session in the end. This presentation was about to be delivered by Professor Panikoulas. Professor Panikoulas is actually the president of the Institute and also the head of the Energy Division. But he also had to be in Brussels, so I'm standing in for him. If you come here next year, he might deliver the presentation himself. Well, I don't know if you will, but... So the talk is basically in 5 sections or chapters. First of all, we'll talk about the cogeneration fundamentals, a few things about what cogeneration is, where the solar part comes into the cogeneration and polygeneration, what the difference is between those two, the hybridization as well of solar with other energy sources. And we'll also talk about the cogeneration facility that we have here at the Cyprus Institute, which I believe you haven't visited yet. You might have been to the Fresnel yesterday, haven't you? No? It's this afternoon. But I think you have seen the presentation from Alarik yesterday talking about it? Okay. So I won't talk too much about it. I have a few slides in the end, but if you have heard about it, then I'll skim them over. And in the end, if you want, we can have a discussion session. Again, I will reiterate, this is not a formal presentation, so if you want to stop me and ask me something, or you want to discuss something about what I'm saying, please do. Now, first, why cogeneration? Well, generally, cogeneration is the simultaneous production of 2 or more commodities from a single plant. Usually, these are electricity and heat, but other modalities exist. The reason we do that is that the source, the fuel, as it's actually on that slide, the primary energy, is used more efficiently. So, does this work? It does. The cogeneration facility is basically this one, the block. You have a fuel which can be fossil fuels, but also can be solar energy, we'll see later. We have 2 commodities that we use, electricity and heat. In the usual modality, you have the electricity production for a power plant, and the heat is usually discarded. So, there are many names that we call cogeneration with. Usually you might have heard it as combined heat and power. It's called CHP. Hey. We also have cooling, heating and power, in case we also have cooling apart from heating and power, which is also called trigeneration. And then we have building, cooling, heating and power, which is called BCHP. This is a great example of what the Fresnel system here at the Cyprus Institute is, because it provides heating and cooling for a building. It doesn't provide power yet, but this may actually change next year or in the next couple of years. The primary energy source, as we said, has been traditionally been fossil fuels, but increasingly there are plants that use solar energy. So the main benefit is that it reduces primary fuel consumption. It lowers greenhouse gas emissions, if we're talking about using fossil fuels as a source. It reduces costs, reduces transmission distribution losses, and considerably reduces O&M costs. And this is probably the most important part about cogeneration, because you use some of the blocks are the same. You'll see later in a few slides how this is happening. Especially the power block from conventional generation and solar generation can be the same. So whatever costs you have associated with maintaining this part can be shared. This is a block diagram, a pretty basic block diagram of what a fossil fuel power plant that uses cogeneration looks like. The main thing is that the exhaust steam that comes, well, actually, let's take each block one at a time. This is the furnace where you have, let's say the heat is produced. You have the heat exchanger, if we're talking about a Rankine cycle where you exchange between, and you want to produce steam. This is a steam turbine, and there you go with electricity. The exhaust steam here goes to the condenser, and they make up water. So all the exhaust steam is basically waste heat. As you know, or as you may not know, I don't know, but your knowledge of thermodynamics, all power plants are governed by the Carnot efficiency. You have a cold, let's say, sink, which is the exhaust steam temperature here, like this one. And you have a hot point, which is the temperature of the furnace, where the combustion is happening. So the efficiency of the whole plant is governed by those two temperatures. This is a theoretical efficiency. You cannot never reach that. But as you can see from this little equation, you can never really achieve the efficiency of 100% unless this is infinite and this is zero, which is never the case. So it's asymptotically towards 100%, but practically the limit is around 65. Now, again, this is the difference between a separate production and the cogeneration. What you have here in the separate production is the power plant, which is a block on its own, and you have also a boiler if you want to produce heat. And the cogeneration takes those two principles and puts them together in one block. A few simple equations. The efficiency of the separate production is the Q here over the power that goes into the power plant, and this is the electric power, this is the heating power, and this is the electric power that goes out of it. And you also have the efficiency of the boiler, which is separate. So you have two separate efficiencies. In the case of cogeneration, these is the sum of these products here divided by the input, the power of the fuel itself. So we're not going to go into the theory of how this comes about, but this is basically the theoretical underpinning of the major, let's say, fundamental way of looking at cogeneration compared to separate production. Practically what it means, if you have a conventional separate generation that has overall about 49% efficiency, which is a quite efficient plant, you have 154 units of fuel coming in, and you have the grid that produces 30 units of electricity, and 68 units are basically lost due to the efficiency of the steam turbine. You also have a boiler separately. The efficiency here is much greater, it's around 90%. So 45 units of heat and 11 units are lost in the process. That's the traditional separate generation. With cogeneration, you can produce the same units, but with much less fuel as an input. So this is an example, obviously. So the overall efficiency is 75%. You have electricity being exactly the same. Those two commodities we want to be collecting are exactly the same. And the losses we have overall are 25. What is the caveat? Why isn't every plant in the world a CHP plant, apart from historical reasons? Does anybody have an idea? Why would that be? No. The reason is that, apart from the technical difficulty, the 45 units of heat here, we have to find a way to use it. I mean, it's a good theoretical concept to use CHP everywhere, but the consumption of heat has to be somewhere that's practical. There has been some retrofitting of traditional power plants where they have pipelines and take the heat, the waste heat from process for district heating, for example, to heat up nearby towns. But the best examples are those that are designed in such a way that the waste heat from the process is used on site or nearby. So these are some sample efficiencies of the processes that you see in power generation. As you can see, the natural gas furnace, which converts chemical energy to heat, is very, very efficient. And as you go down, the internal combustion engine, for example, that you have in your cars is pretty inefficient. You have chemical to mechanical, even though this number is probably a bit higher in modern cars, but generally it's around 30% or less. The power plant in a boiler, again, is very, very efficient. The steam turbine, it's somewhere around there, 40-45%, depending on the size. Larger plants tend to have slightly higher efficiencies. The generator is highly efficient. As you go down, you'll see that renewables down here, or the geothermal or the wind, PV cells or the ocean thermal, are less efficient and are prone to intermittencies. The cogeneration part, basically we are mostly interested in these three operations. We have the power plant boiler, which is chemical heat, the steam turbine, electricity generator. These are the three efficiencies that we are interested in, and these are the ones that govern the cogeneration principle. There's two types of cogeneration. The first one is called the topping cycle, and the one is the bottoming cycle. Basically, the topping cycle is a system that produces electricity first, and then recovers the excess thermal energy for other applications. This is how the cogeneration CYI system works. What you have here basically is that you have an engine here, and that's the traditional generator which goes to either the building or facility or the grid. Then whatever exhaust gas you have is used in a heat recovery unit with water, and then provides the auxiliary, the secondary commodity in cooling or heating. And this is the most usual example. This is the topping cycle, which that's what you see more usually. At the bottom here, you have a process which fuel is combusted as a part of the industrial process, and then you have waste heat, and that waste heat then is used for electricity generation through a turbine. This is probably, if you want to be very strict, this is not really a cogeneration diagram, because you would have to have some sort of arrow here showing that the heat is also used in the cogeneration modality, let's say. But the takeaway point here is that you can retrofit systems which are that are designed basically to provide heat for industrial process, and then from that industrial heat provide electricity as well. But the share of these systems globally is much less than that. It's about 10% of the systems are like this, and about 9% using the topping cycle. And all new systems designed for cogeneration use the first one. The second is usually an afterthought of processes that belong to the industrial sector, and they want to improve their efficiency by adding a turbine in the end. Now, let's see where the solar part comes in. Okay, first, do you want to ask any questions here? Because we have some sort of, yeah.
Two slides before.
This one?
And this one, the gas turbine, mechanical, 35 and 40%. What's the fuel, LPG?
Sorry, were you referring to which one? This one here?
Down. Yes,
here.
LPG?
Gas could be natural gas.
The top is not a furnace.
It's the furnace. This is only about producing heat. This is a turbine. That's the difference. From the chemical energy which is trapped into the fuel, producing heat is efficient basically by burning it. But here, when you want to convert it to mechanical, you have to include a turbine in, so that's where the losses come in. Okay, these are ballpark figures. You can have actually gas turbines which are more efficient than that, and usually they are a bit more efficient than steam turbines, depending on the size, of course. They also have other advantages. They're a bit smaller, a bit cheaper. They also start up much faster than steam turbines. They can also be used in cogeneration plants easier. But anyway, this is a different discussion. So, yeah.
So what is the difference in terms of capex between the top end and the bottom end?
It depends. It depends a lot. Generally, I would say that the topping cycles are more efficient, and so the capex is for each. It depends on how much electricity you want to produce and how much heat. But if you want to design a cogeneration system that has some sort of equals, then you would use the topping cycle. Yeah, this would be cheaper. I don't know exactly the numbers, how much, but I would think that it is between 10 and 30 or 40% cheaper than what this would be. You will rarely see systems designed with a bottom cycle for cogeneration 100%. You will probably see systems in industrial processes being retrofitted to produce electricity by adding a turbine in the end that want to increase the efficiency of the whole system, but it is not usually the most efficient way to go about it. And in the last 10, 15 years, I have the data somewhere, if you want, I can send it to you. Most of the systems, they're predominantly, almost the lion's share, almost like 95% of them are topping cycles.
Probably they're not also really comparable because you choose one way or the other depending on, I mean, if you're doing the bottoming cycle, probably you need high temperature heat. This is why you do this. So there's a different application.
Yeah, because the waste heat has to be of high enough temperature to produce electricity, unless it's using organic ranking cycles, things like that, which are really inefficient. But yeah, Luca's right. So you have to have a process which has enough temperature, and the temperature here of the waste heat is of high enough quality to drive an electricity generation cycle. Is that correct, Luca?
I mean, this is my opinion, because as you pointed out, probably in the bottom figure there is 1 hour missing. You do this because you're cogenerating. So you produce high temperature heat, you use a part of this high temperature heat, and a part is used to produce electricity. So probably you need this, you do this when you need a high temperature heat source for any other applications. And then you cannot use the topping cycle in that case because you will get lower temperature heat as a waste heat from the thermodynamic cycle.
Yeah, that's right. So, shall we move on? All right, so let's see what the cogeneration and polygeneration from solar sources are. You know about this, I think, already, but let's go just for a quick review. PV, obviously, storing electricity from PV that produce electricity directly is not trivial. The predominant technology is batteries. We briefly touched upon this on day one. Other, of course, ways exist, but this is, let's say, the mainstream option. Solar thermal technology convert radiation to heat. It's easy to store. It can be used in a wide range of applications, electricity generation, desalination, solar fuels. We'll be talking about that a bit. But solar system can be more complicated and more expensive to install and operate. So we'll be talking about cogeneration using solar heat now, solar thermal processes. Have you come across this chart at all? This is the theoretical maximum of solar heat engine, the efficiency. Remember in the few slides back, this one here, here, that we talked about the Carnot efficiency. We have this, let's say, theoretical ceiling that we cannot go through. Now, this is basically the Carnot efficiency, this curve up here, the blue one. This chart is from Fletcher and Moen in 1977, a paper back then, but obviously the Carnot efficiency is a concept which is quite old. The C here denotes the concentration ratio, how much concentration you can have from each solar concentration technology. The troughs, which have the lowest concentration ratio, can have an ideal solar heat engine efficiency that only reaches about 45%. The solar towers, which have a high concentration ratio for about 500, or even higher sometimes, approaching 1,000, correspond to this curve here, which is a little bit more than 60%. And the dish systems, which you may see having a Stirling engine in the end, can have a concentration ratio of about 2,000. So this is the main reason why trough systems are becoming more popular lately, because there is by solving all the engineering problems that we used to have in the past, we are approaching the level that we can utilize the theoretical maximum of the heat engine that the towers can produce much more closely to the theoretical maximum. Obviously, we cannot reach such high levels, but we can exploit the potential under this curve more than what we can under the curve of the parabolic troughs. So keep that in mind, that when we talk about different technologies, you have this ceiling for each technology. Why hasn't this picked up commercially? Have you talked about solar dishes at all in the last few days? Yeah. Well, yes, you're on. There's difficulty with storage, a lot of difficulty with storage with dish systems. They're also more expensive and difficult to deploy in large quantities. Possibly expensive as well. Let's see if these problems will ever be solved. This is the the concept of solar power plant. Let's go again through the fundamentals. We have the solar radiation, have the concentrator here, and the receiver. You have, from the receiver, you have the thermal storage here, which basically runs around in this loop. And you also have the fossil fuel or biomass auxiliary boiler, which is supportive. And you have a power block here. This goes to a generator and produces electrical energy. This is not a true cogeneration concept, however, even though you have the auxiliary boiler down here, which is run by fossil fuels or biomass. It's actually cogeneration, but it cannot be called a true hybridization concept. We'll discuss that in a few slides. In the case of cogeneration with solar processes, hybridization and polygeneration, the thermal process that you have in the previous slide here, basically producing electricity, now can be substituted with all these different services. It could be electricity, but also be solar fuels, soil desalination, soil detoxification, oil recovery, mineralogy, and many applications. We'll talk about these, or at least some of these, in the next few slides, but I think you will go into detail as well with Luca's presentation after mine, where he'll be talking about some of these other services. So, in addition to the classic electricity generation modality, you can have, as I said, desalination, disinfection, and detoxification. You can have solar heating and cooling. You have solar fuels and chemical energy carriers using hydrogen, syngas, etc. You can have cycles for chemical storage of solar energy. This is the zinc oxide cycle. I'll show you a slide later. Process heat as well. Also nanomaterials, fullerenes, nanotubes, and ceramics, and other exotic materials that you use mainly in solar furnaces. Also material synthesis and aging behavior, and ceramics, glass, and all these things have come about and have become let's say a parallel market or a parallel activity to the mainstream electricity generation. So let's take the first one, which is probably the most well known. It's the solar cogeneration of electricity and water. Now, most solar large thermal desalination units are combined with power plants. The reduction in efficiency of electricity production, that's what they cause. And they also, by using solar, you can reduce the energy discharge of the ambient. You require a smaller cooling loop. Now, let's take a look at these three modalities where you have a solar field and how do you do desalination. The first one is you have a solar field here and you combine it with storage, and the heat goes to an MED. Do you know what MED is? It's the multiple effect distillation unit. It's a way of desalinating sea or brackish water. This requires power from the grid. This is the classic heat-only modality, and there are many plants using this, especially in the Middle East. Now, if you have the power-only option, so you have a solar field which doesn't connect directly to the desalination unit, but goes to the power plant itself, and you have, in addition to fuel, there's also a parallel loop of storage. And the power plant itself then drives an RO unit. Does anybody know what RO is?
Reverse osmosis.
That's reverse osmosis, correct. Well, do you know the difference between MED and RO? What the main differences are? Anyone? Well, the RO is a mechanical way of desalinating water. It's basically a membrane where you push the saline water through, and the membrane collects, let's say, the salinity of the water, the salt, and whatever comes on the other end is desalinated. It basically uses mechanical power. So that's why a power plant is more convenient here, and that's why you can have an RO system coupled with other renewable energy sources that produce electricity, PV or wind. An MED uses heat. MED basically has different stages of evaporation, so you have your saline, your seawater in one tank, which you heat it up with heat that is usually not very high. It's around 100 degrees. The steam from evaporation that produced in the first effect, as it's called, is driven to the next, and then this process goes on, and the number of effects that you have determines the salinity levels, let's say, of the final product. What you can have is a combined heat and power that also uses an MED unit, but instead of actually having as here the solar heat directly into the MED, you provide the solar heat into the power plant as an input, and then the power plant drives the MED, but also uses part of the heat. So it's kind of a combined procedure to desalinate water. This is the cogeneration modality is something that we have kind of developed here at the Cyprus Institute, but not exactly like that. I'll show you the difference in a while. So let's say the desalination is one of the main other market activities that solar systems can have. The other one is solar fuels, or one of the other ones. It's not strictly cogeneration, but the need for high temperatures can produce several byproducts, just like a syngas or several metals. And some of the tower systems can be retrofitted with furnaces. This is a dedicated solar furnace, which is situated in the Pyrenees in a beautiful location in the south of France, which is not there for producing electricity, but it's there for collecting the solar radiation and increasing the heat in this tower here to very, very high levels, about 3,000 degrees, somewhere there. That heat is not used for electricity generation, as I said, but it's used mainly for material science. So it's a facility that has been there for quite some time. I think it was built in the 60s.
I think it's the first facility.
It's the first, yeah. They also have some smaller furnaces which you cannot see through that, and also some other solar labs in the CNRS here in Odeyo. But this is the largest in Europe, and it is one of the main research infrastructures for solar energy in Europe. Another option is the chemical storage in zinc oxide. This is taken from work that has been going on in ETH and PSI, that's our colleagues in Switzerland. They're trying to see whether we can use zinc as a storage medium. So you have here a solar field which has a beam down reactor here, which uses something like a hyperboloidal mirror, I think it's called. It goes down to a reactor chamber that basically produces zinc, and the zinc itself has can have several byproducts which are useful. Apart from producing electrical power here after a series of chemical reactions, you can use hydrogen, which then combined with carbon monoxide here we can use as syngas. Syngas is something that can be further processed and converted into fuel. So it's still in the, I would say, I don't know how early the research in this here, but it's a concept that is workable, and this has been a project that has looked into the feasibility of systems like that, whether they can be used as a storage solution using chemical storage, basically using solar energy. I think you'll be having those slides in the end of the school, so I've put a reference here. It's called Solzing Project, so if you click on that you can go find more details about this. The PDF that you'd get in the end will have these live links as well. Again, you have CSP for electricity and hot water. These are slides taken usually from a company's presentation, but this just to showcase that you can have PV with solar hot water as well. The heat that the PVs are producing while they're operating, you can recycle that and use that for usually building heating. As you know, PV cells don't really work well with temperature, and they want to be cooled. These are other systems of using solar hot water. But the main, let's say, research direction that we're interested in, and many of in the research field of solar energy are going, is to use STE for process heat. STE meaning solar thermal energy for process heat, and this acronym is called SHIP. Now, 66% of the heat generated by fossil fuels is, 65% of the heat generated is from fossil fuels, and 45% of it is used in industry. Now, this is about 30% in final energy consumption in Asia and Latin America, and then around 20% in non-OECD Europe. These are some statistics there the point here is that we have a lot of heat being used in industrial processes around the world, and it's all driven by fossil fuels. The SHIP modality presents a modest, a small share of about 88 megawatts thermal, and only 0.3% of that total install is of it is solar thermal capacity. It is close to competitiveness, but only low temperatures for the time being. And even though it's a direction that everybody's talking about, that we should be using solar heat for industrial processes, it seems that it is not reaching its potential that it should. Typical applications would be drying, curing, and pasteurization of dairy products. And there's been an initiative driven mainly by the European Commission, and we are actually part in a Horizon 2020 project, I think in AIS as well, called InShip, where we're trying to harmonize the standards and give access to the research facilities around Europe and synchronize the ship research. Because we think that this is an area that, apart from being exciting scientifically, is something that is a very viable direction for solar technologies to take away from electricity generation and going into the industrial process heat. This is also some live links. When you get that, you can click through the InShip project, you can see more details. But also, I've put here a database of solar heat process for industrial purposes. There's a database of plants around the world. I think it has more than 2,000 now, but it's mainly small systems. And you can, there's also a way to sort them by country, by continent, by technology, by what sort of industry they are applied to. So you can see whether they are, most of them are in these areas that I've just mentioned, in pasteurization, drying, and curing, but increasingly there's applications in other areas as well. Just a few examples. We have the CSP for oil recovery plant, solar concentrators. There's a big company behind that in the States that is driving this procedure. This is a picture of, I think it's dairy products unit, factory, I would say. I think it's in Switzerland, that uses parabolic troughs on the roof of the building to assist its industrial cycles. So that is a kind of an overview of the solar polygeneration. So let's move on to the solar hybridization now. This is mainly the hybridization of existing power plants with solar cycles, let's say. So large CSP plants usually have large backup fossil fuel units for dispatchability to prevent freezing and to ensure faster startup. Prevent freezing of what? Does anybody know what prevent freezing of is? What do you want to prevent freezing of? Exactly, yes. I mean, that's what you have when you have storage. And you don't want the storage medium to go under a certain temperature. You have a fossil fuel backup generator where you want to keep the temperature high enough to prevent freezing and solidification. Actually, in our unit in Proteus, the molten salt freezes at, I think, at about 230 degrees. But we don't have a fossil fuel backup generator. We actually have electric heaters which are embedded into the storage tank. And these prevent and most of the energy that basically goes there. As a net overall, it doesn't produce anything. It's a pilot plant, I'll show you later. But especially in the beginning, where we didn't actually have all the heliostats connected, most of the energy was going to heating the salt and preventing it from freezing. Full hybridization refers to the process of integrating a solar thermal plant, or parts of it, into an existing thermal process, usually for electricity generation. You have plenty of modalities in the world, with natural gas, with coal, with biomass, but also with PV and wind. This is an example of a solarized gas turbine. You have a solar input that can reduce or eliminate the fuel consumption for combustion. You have a fossil fuel system here and a combustor. And this goes to the recuperator, which is optional, and a generator. And you have here the concentrated sunlight, secondary optics, and the receiver. So the cycle here is the fossil fuel system is not used as a backup of this, but this is used to augment the processes of the fossil fuel system itself. You can design a system to have a CSP cycle from scratch, let's say from zero, but you can also retrofit existing plants with solar systems, and this is a direction that I think that is not taking enough merit for the time being. An example of this, of such a system that has been built with the option with the idea of having this as a default generating system is, I think it's in the States. It has been operating since 2012. Now, in electricity plants, the Rankine cycles integration can be in lower temperature steam, at about 400 degrees, which is best served by parabolic troughs and modern oil cycles. In medium steam, between 380 and 450, you can do Fresnel superheated steam or parabolic trough direct steam generation. In higher steam applications, higher temperature, which is served better by the tower system configurations. Also concentrating, also dish technology has been considered, but technology and the integration is still unproven. The steam reheating, which is also another part of the hybridization plants, can be done by Fresnel or parabolic troughs, and the feed water heating, again, the lower temperature by Fresnel systems. If you're taking notes and I'm going too fast, please let me know to slow down. But you can have these slides, of course, in the end. Now, with natural gas, the systems have actually a name for themselves. They're called Integrated Solar Combined Cycles, ISCCs. So the idea is to boost the output of the heat recovery steam generator. The principal advantage, as I said earlier, is to have this hybridization of solar powers to directly set off the fuel energy without having to pay for power block or transmission lines, because they are already in place. You have built a natural gas plant and you're supplementing it with a solar cycle, and you're taking advantage of the fact that the infrastructure is already there, your operation maintenance schedule is already there, and the additional cost is minimum. Now, if you want to share a power block with fossil fuel power, it greatly increases its utilization, as we said. And since maintenance personnel is already on hand to monitor and maintain the power block, the costs associated with that are reduced, or even actually reduced down to zero. Here's an example. Sorry for the quality of the graphic here. This is a solar field, again, which is using a tower modality, and you have a hot tank and cold tank for storage, which basically is embedded into this natural gas cycle, where you have all these reheaters and all the high pressure, low pressure, and medium pressure units of natural gas, which basically goes to the steam turbines up here and the generator. And what's really happening is that the steam, the temperature, the solar steam generator here increases the outlet temperatures, so in order to improve the efficiency of the whole plant. And if you do a techno-economic study, you will find that for some of the cases anyway, the size of the solar field here required to improve the efficiency for 5 or 6 or 8%. The amount of money that you're saving in fuel actually pays back the solar field in like 5 or 6 years, or maybe even less, depending on where you are and what sort of DNI you have. It's also, the CCGT plants allow the integration of steam in various stages, as we said, in high pressure steam, in the high pressure steam here, the high temperature steam boost, the low temperature steam boost again in 350 degrees Celsius. Again, going down to lower temperature to about 260. Most ST technologies are suitable. The actual integration of functions of many parameters. But the best performance perhaps is for high temperature by solar tower systems, as in this example here. And lower temperatures best served by Fresnel. These are not hard and fast rules. You have to look into each case individually and run a simulation and see what works best. But the deployment of solar ST technologies for hybridization of existing fossil fuel plants has mostly been done around parabolic troughs. There are many reasons for it. The principal one is the technology of the parabolic troughs themselves is the most mature, so it's something that the developers are more comfortable using. But it's also that the high temperatures that the solar towers produce are not always necessarily a good thing. This is another example of the integration of solar system with coal. Now, the integration of Rankine cycle plants is relatively straightforward. Well, this is taken from a recent paper from from these people here, I'm not Dalby, Pants and George in 2015. They have published this paper in the Nature Climate Change journal, which is quite high profile. And their argument was that you can have an integration of all these solar cycles into many parts of the cycles of a coal-fired power plant. There is really no technological argument that goes against doing that in many cases. The points of integration can be the preheater, the boiler, the economizer, and the superheaters, which basically down here, here, there, and there. And the temperatures of preheating vary, and the concentrations of about 20-50 seem to be more optimal. So this is, they have found out that these concentrations correspond better to technologies that serve these concentrations, which is most usually parabolic troughs or Fresnel, but parabolic troughs, being more mature, is something that these developers would find easy to use. And there have also been some developments using solid particle receivers. They are preheating the boiler combustion air, basically here, where the boiler is. This is more experimental. I think there's also been some European money behind the project trying to investigate this probability, but doing that in the Rankine cycle, augmenting the steam temperature in various parts of a coal-fired plant is not that hard. And some people have done it. And this is a block diagram of, simplified obviously, of the coal-fired plant called Cogen in Australia. If you go and look at those wiggly lines that go into the power plant themselves, you'll see that basically they're using a Fresnel system. The hot water that goes into the plant and into the boiler is helping that to increase the inlet temperature and effectively raises the efficiency of the whole plant by making the distance between the hot and the cold point larger, so effectively increasing the efficiency of the whole plant. So it's been done. It's not that hard, to be honest, but you need plants in an area where the DNI is adequate enough to do it. Also, you can do that with biomass. Instead of having coal, as you have here, this is the coal line that goes into the burner, you can burn forestry, energy crops, farming waste, all sorts of materials. This is a block diagram of a system which already exists actually and has been built in Spain. It was commissioned in 2012. I think it's in Lleida in Catalonia in Spain. It's 102 megawatt thermal, out of which 56 is solar. They use a parabolic trough system. 36 is biomass, and they also have a 10 megawatt natural gas backup, which is here. This is the biomass boiler. This is the natural gas auxiliary gas boiler. So the solar field runs through those, let's say, increasing the steam, the inlet temperature. This is the electric component where you have the turbines, the high pressure turbine and the low pressure turbines. And this is the balance of plant, the classic, let's say, generator in the end. As you can see, this plant doesn't employ storage. It uses the solar heat to produce electricity throughout the day, and it uses the biomass burner for all other times, at night, or when it's cloudy, or when in the evening. They have thought pretty well about how to size that. So as you can see, the rated power of the solar part is larger than the biomass. Of course, the capacity factor of the biomass burner would be higher because it can burn almost all the time. But they have managed basically to have this plant operating 24/7 and providing good chunks of electricity for the local community. I don't have exactly the numbers of how many megawatt hours it produces, but it's the capacity factor of the whole thing is around 40%, 45%, somewhere there. So it exists. It's possible, it's doable, and 100 megawatts may sound a lot. It isn't really. You can actually have systems which are smaller, but it's a direction that hybridization is also taking. So, as overall observations about this hybridization and polygeneration thing, You can reach low LCOE. Does anybody know what LCOE is? Yeah, you know. I know that you know because you work with it. LCOE is the levelized cost of electricity of energy. Tomorrow, actually, in the lecture tomorrow, we'll talk in detail about how this is calculated. You can have, because many components are shared, you can have lower operation and maintenance costs. The thing that I was mentioning earlier is that the solar hybridized cogeneration is not receiving due attention. That's my opinion and some of the opinions that for people that write about it. It could be a great way of utilizing mothballed infrastructure from coal and oil-fired plants. The energy transition, which is now the very hot word in Europe, of going to 2050 with a system that is basically clean. We're using mostly renewables, and we're slowly going to be phasing out all fossil fuel generation. Will require some profound changes. And it's not certain that we can do that with stochastic renewables. We cannot use only PV and wind. We will need some sort of way of having baseload generation, and this is actually quite a good way to do it. In the beginning, have existing infrastructure. In Cyprus, for example, you have lots of oil-fired plants, and you can have those hybridized with solar, and gradually have them take over the role that these plants used to have for the last decades, maybe centuries. Now, it contributes to baseload generation, as we said. It allows deeper penetration of stochastic renewables, because if you have a larger base of baseload generation from a stable producing electricity plant, then the penetration of something which is not predictable, that's what stochastic means, is easier. It offers stability to the grid, and you can also use those services that these plants offer in a liberalized electricity market with day-ahead generation, auxiliary services, etc., etc. But it's still at the early stages of maturity. As we said a couple of days ago, technology sometimes surprises us. It comes quicker than we think. And policymakers don't sometimes miss the profound changes that technology can make. There's a limitation on the ISCC projects which depend on the extra capacity of existing power block, because sometimes you may have solar generation producing more than what the power block was able to absorb, and sometimes it makes sense to upgrade that, but this is a case-by-case thing. And for now, it's complicated to reach a deal on supporting these things, because they don't really fit easily into the existing support frameworks. Tomorrow we'll talk about what the difference is between a PPA and an FIT. The PPA is the power purchase agreement, and the FIT is the feed-in tariff. Now, a few reference plants. This is a natural gas CSP plant, which is a 10 megawatt thermal. Another plant system which is called HySol. You can find lots of documentation about it online. This natural gas parabolic trough is called Kuraimat. It's actually this picture down here. It's very interesting because you have the back of all these parabolic troughs, and you have this huge coal-fired plants in front of it that not only look strange, but the soot and the dirt around this area is amazing. If you go there, have you been there, guys, in this plant, in the Kuraimat plant in Egypt? You have, yes. I have too. I was there about 3-4 years ago, and I found it very strange that actually you had to clean the mirrors every day in order to avoid this. But it's a very interesting plant, and the people that run it are quite knowledgeable about it, and it's great that actually Egypt was one of the first that built it. There's also a large plant in Algeria. And the largest one, which is the one that I was referring to earlier, is called Martin Next Generation Solar Energy Center. It's 75 megawatts thermal in the US. This is the biomass plant that was this here. This is a picture of it. That's in Spain. And the Cogan Creek plant in Australia, which uses coal as the main fossil fuel source. So this is a pause here for let's say, the 2/3 of the presentation. Any questions before we move on? No. Now, let's talk about a bit the cogeneration facility that we have here at the Cyprus Institute. The whole thinking behind doing a cogeneration facility started about 10 years ago, one of the main drivers, the main motivations behind it was the vulnerability of infrastructure that we are experiencing here. This is a picture of the main power plant in the island, which was, I wouldn't say partially, but mostly destroyed in 2011 after an explosion of an ammunition depot in a naval base which was next to it. I was on, I think, on the 7th of July 2011. I can't remember exactly the date, but it was summer, it was in the morning. And the explosion of the ammunition depot took away most of the power plant, and Cyprus, even though to its credit, actually, we didn't have too many blackouts, we had a few brownouts, but generally the system stayed as much, it absorbed the blow in the best way that it could. The local operator went into panic mode, but eventually after a year all the problems have been solved. This has been rebuilt now, it's actually quite new, but it showed that if you have power generation concentrated at one point in a country which is so small, an event like that can destabilize the whole economy, the whole island. The other thing was the water shortages. In 2008, we had to import, we meaning Cyprus, we had to import fresh water from Greece in tankers because there was such a severe drought that the natural reservoirs and the dammed reservoirs that the country had were not enough. Ever since then, this has been partially mitigated by the building of desalination plants. But back then, about 9 years ago, this was also a severe issue. So the Cyprus is developing a cogeneration system of electricity and desalination, but it's not the classic type that tries to target larger markets, but we're trying to do a system which is mostly targeted towards smaller, isolated and rural communities. And this is a GIS map that we have created in a study that it's actually still not published, it's a draft study, for the appropriateness of the technology. We're using basically a few indicators based on electrification, water stress, and cost of population density to see where these technologies that we're developing here can be deployed. We're looking for robust, we're looking for hilly terrain, corrosive coastal conditions. These are the things that we are addressing. And we're trying to see how this thing can be differentiated from alternative solutions like PV, NRO, and things like that. This was the study that started it all in 2011. It looks complicated, but it isn't really. The next slide will actually simplify it a lot. We developed a cogeneration scheme of integrated thermodynamic cycle, joint optimization of power and desalination subsystems, and the utilization of harvested heat. This is the power block here. This is the MED that we discussed earlier. We also had plans to use an RO, which actually now have been scrapped. And this is taken from a paper in 2011 that described all the processes. How it works is basically like that. You have the solar field, and the difference to the classic MED with solar modality that I showed you earlier is that the heat for desalination is taken directly from the storage. The storage is basically the central node of the whole system, and the solar field and the receiver and the storage operate as one. The same fluid runs through both in a continuous fashion. The storage acts like a thermocline. So you have a production of electricity, obviously, but the heat from the storage and the rejected heat from the operation of the power plant are both driven into the desalination unit, which, as I said, uses MED, and we generate desalinated water. The advantage of that I only realized, of course, when the power and desalination cycles are integrated thermally and optimized together. So for that, we have a facility in close to Limassol, which you haven't visited yet, but you will. It's actually running now an experiment. It's called the STEPI-W, which is solar thermal experiment production of electricity and water. It is not a commercial facility, so it's not supposed to be producing commodities to sell in the market. But it's to prove the concept that we have developed here. We have used heliostats, these mirrors here. I think Aris Bonanos gave you a lecture yesterday about heliostat technology, so you know about it now. Thermal storage is in molten salts. and we basically take the heat from the rejected heat from this process here, and move it down to the MED. This is a bottle of water, and this is electricity. So that's the main thinking behind it. And this is how the facility now looks like. It's obviously close to the sea, because we want to have seawater coming into the tower and to use as a feedstock for desalination. This is the heliostat field, and this is the tower where we have the receiver up here, and which is also connected to the storage, and the whole integrated concept is called iStore. And this is a room for control and offices. This is the PV park, which we had plans to use to connect that basically and have an RO and reverse osmosis system run by photovoltaic panels. Unfortunately, during the early development phases of the park, the PV panels were stolen. So we have kind of abandoned that experiment. But we may actually connect in the future. There's also a few more buildings which are built for other purposes for the energy group. This, as I said, is situated near the coast, near Limassol. The village is called Pendakomo. It has 50 heliostats, about 5 square meters each, actually a little more than that. The heliostats were built with an agreement with CSIRO. CSIRO is the scientific, well, I'm not sure exactly what the acronym is, but it's the main state-funded research institution in Australia. And they have also a branch that is doing active research on solar technologies. And these heliostats, these are the back of them, are built by them, or with them, I should say. It has a rated power of 150 kilowatts thermal, which basically means that this isn't really suitable for commercial deployment. It's too small. But the multi-stall storage has a 15 hours practically capable of continuous operation. And the integration of the receiver and the storage, which is called iStore, is also patented. It has an integrated MED desalination model. Again, this is the graphic that I showed you earlier. So what you have is the solar field, which is this one here. That goes to the receiver. The receiver is number 2 up here. The receiver is, again, is a design that we did here at the Institute. And you will see that. You will go up next to it when you visit the facility. This is a storage tank, which is this part here, number 3. It has been built with the help of a company from Italy. They have their offices very close to Casaccium, where their offices are outside Rome. And this is the MED facility. What you actually see here is the prototype MED effects that I talked about earlier, which were used as a proof, let's say, of that the concept works. And it's the main output from a PhD student that we had here. This is the actual unit, which has larger effects, and it's now installed on site. It's actually down here. The steam generator is very small. Because of the small size of the facility, it was practically impossible to find a steam generator that had an efficiency worth talking about. But we have it there just to show that the power can be produced. But as I said, it's just a proof of concept and not a commercial facility. This is how it looks like from a photograph, but this is how it looks inside. You have the receiver up there and the storage. The hot oil comes down into the storage and then goes back up into here. So there is no heat exchanger anywhere. The same heat transfer fluid that is running in the receiver is the same thing that runs in the storage as well. So if you go to the tower, or when you go to the tower, you'll see basically this configuration. Sorry. Yeah.
Is it one tank storage?
Yes, it is. It is one tank. It's the thermocline, yes. I won't go into details because I know that you're interested in this because we have dedicated this whole session for storage next week. I think that you should talk about this when you actually visit the facility. There's pros and cons, and we have actually run into several issues of running the thermocline like this. It works, but it's very temperamental, let's say. Let's put it this way. Now, this is a video, actually a time-lapse video of the installation of the heliostats. It isn't very long. It lasts for about 2 minutes. So, oops. Let's try and have a watch, if we're allowed. Why not? No, it doesn't allow me to click on it. Ah, there you go. So this is, we installed a camera on the top of the tower, and had it, taking shots while the whole thing was being installed. Oh, I didn't know there was music too. Oh, nice. So these are the heliostats arriving, and there's the Cyprus day and night cycles. These are the laboratory that actually is in the basement of the building that you saw. Oh no, you didn't see yet. But the third building on the north of this one, where we have actually a laboratory where we do the canting and the preparation of all the mirrors here. So they were built on those bases, and they were fixed to the let's say foundations. So we use local contractors to build all these facilities here. This is from the back, to build all these in the specification that we wanted. And this is the tower from inside. Yeah, this is the receiver. It's being shipped. It's being hauled up into its place. These are the inlets for the different piping and outlets. As you can see, Cyprus is a pretty arid land. It has issues with water availability. So again, this is a receiver. Yeah. This is the tank for the storage, and this connects now. This is the pump, the main pump, and over that we have the receiver sitting on top. Yeah, the logo. Okay. Yeah, this is how the construction looked like. Now, for a bit of the economics of that system. Sure. Yeah.
I think we will have a chance to ask another question, but the choice of building it with steel, was it like for a particular reason, or like to build the tower? It's a steel structure.
It's a steel shell. It's cheaper. It's cheaper and it's easier to. I'm not sure exactly. I wasn't involved in the process of actually building it, but I think that there's a provision of actually go higher, and I think this is the reason they did it like that, because it's more modular. You can build more things on top. Yeah, sorry, I can't answer this question. Aris will know for sure because he was involved since the beginning, but I wasn't.
I think it's a very complex issue.
Yeah.
It was dealt in dedicated presentations or places. I'm not an expert as well, but for what I could get from this presentation, there is no clear winner today. It depends on so many factors, also on the cost, of local cost of working force and so on. But there are several tower building designs that can not only steel and concrete, and it's I would say it's an open topic still. I don't know.
Jeff, if you have any.
It's not easy to get an answer, but you can look for this presentation, you've been to Solar Basis, so you can download the presentation and the paper. Probably you can find more information on that.
Well, it's a good question to pass on, or to actually have an answer for next time we see each other tomorrow. I can ask around and then come back with an answer. So this is just a very small slide about economic analysis. This is not for the system that you have seen, because the system that you have seen doesn't really perform economically very well, because it was built specifically to host an experiment and not really to be commercially deployable. This is an upscaling of the system to 4 megawatts electric and not 150 where it is. Actually, it's 50 kilowatts electric now. It's 150 kilowatts thermal. But as you can see, from the basic cumulative payback cash flow, you can see that the payback time is about 8 years, and the NPV is positive at 19.1 million euros. We don't want to be banging the drum of the system being very cheap and all that, because the whole study was under the assumption that there was a feed-in tariff for electricity part, which was 26 cents, euro cents per kilowatt hour. This was when the study was done a few years ago. This support scheme doesn't exist anymore, and it will never come back. I don't know if, George, you want to add something to that, but I don't think it will. So if you actually did the same analysis with this upscale system, 4 megawatts, with what you will probably get from a PPA now, this will probably shift around to 16 or 17 years. So it's not outrageously expensive, but it's still, it's not in the same ballpark as PV. It may come down though, and we are actually in the process now of doing that study, which this slide here is part of. We'll have that study ready. We said that by Christmas, but we'll see if it's going to be ready by Christmas. Then we'll have a better idea of what the prospects are, what the markets are, and what the cost we're trying to achieve is to have this viable. This is the cash flows. I won't go into details. We'll talk about these things tomorrow. This is, again, we also run a kind of a risk assessment of the various cost elements. So we use a kind of a Monte Carlo approach, which has samples. I think we use 50,000 samples for this one, to see how the NPV would go, depending on how the variations of the various inputs that we used would go. And I think that Professor Blanco, who's going to be here tomorrow, is going to be talking about this approach in more detail. I think we are sharing the presentation tomorrow. I'll be talking about the basics for an hour, and then he'll talk about this for about the last part of the talk here.
What does NPV stand for?
NPV, I'll talk about this tomorrow, is net present value. The net present value ideally needs to be over zero. It's an indication of the profitability of a commercial, let's say. If a project is commercially viable, you assess its performance by looking at some indicators. One of them is the NPV. And if it's over zero, then you say that, it has good prospects of going ahead. If it's less than zero, it means that your future earnings are going to be less than what you're spending now. So maybe not such a good idea to do it. As the final, let's say, few words, this is the Fresnel facility that you saw yesterday. So I won't be talking about too much detail. You'll also be visiting this facility today. This is the main block diagram. And actually, this is a screenshot of the control system that we're using, which is using this sorter system platform. So you have the Fresnel here. You have an expansion tank. But for oil and for water, actually, next slide, I'll show you which ones they are. The main thing is the storage tank here, which basically holds pressurized water and can operate the facility for 4 hours in the winter and 2 hours in summer, independent of weather conditions. And in the end, you have an absorption chiller. And, you have seen this yesterday, haven't you? You saw about the system. This is just a very, very quick overview of the different subsystems. This is obviously the Fresnel collector. It's rated at about 50 kilowatts thermal. It was financed by an ENP ICBC MED project called STS MED. There are 3 more systems like that. One of them is in Italy, one of them is Jordan, and one of them is in Egypt. Not exactly the same technology. The system in where is it? In Jordan uses parabolic troughs, and I think the system that you have linear Fresnel, the same thing as Sicily and ourselves. So this is it's Sechem. What is the
STS, the project.
The project I know? CCAM, right? Okay. This is the storage facility. This one here, the biggest tank of the three. It holds pressurized water, and the highest pressure it goes is about 9 bar. This is the building it's serving, because it's the energy it produces. It's used to cool and heat the building, which is this one, the NTL as we call it. And at the back of that building, which is not seen on this picture, you have the absorption chiller. This is the absorption chiller. This is the cooling tank, the cooling tower, let's say, of the absorption chiller, and it's all connected through a piping network that goes through that building and under this bridge and connects all these subsystems to the chiller there. Maybe it's not the most optimal solution, because you have lots of energy losses in the traveling of the hot water between the back and the front of the building. But at that moment in time, it was the best thing we could do. This building does belong to us, actually. Let's go back. This belongs to the Ministry of Labour, and there's a school housed in it. We may actually get it in the future, but if we had it when we built the system, we could potentially build the absorption chiller somewhere much closer, but practically this is what we did. So, with that, thank you very much. So, I don't know what time it is. We are... Yeah, we have about 15 minutes spare for discussion if you want. So, from all these things that we had talked about, anything to mention, ask? Yes, Jeff, please.
Are you able to comment on why the thermocline system has been invented?
No, I'm not going to answer this question. No. First of all, I'll leave the experts to do it, because I'm not really an expert in storage. And secondly, it's... I don't think this is a related discussion we're having about cogeneration in general here. This is something that has to do with storage and the Protea system itself. I know that a bit through the grapevine, because it's not first-hand information that I have, that the operation and testing and characterization of the system has been very hard. Lots of technical difficulties that ranged from burst pipes to insufficient insulation to these thermal sensors that you installed, they weren't working, and we had to ship them, half of them back, and and so we didn't actually have data. We didn't know what was going on. So it was plagued with difficulty. The team that works in Pentakom, and I'm not one of them, I'm usually here at the headquarters, let's say, was having a torrid time for a year trying to make it happen. I know that they have worked with it, and I think it's working now, but I don't know if Evgeny, do you have any information about this, about whether the thermocline, about the storage and the receiver, if it's working? So yeah, it's maybe we should wait and talk to Aris or Panikolas or Manuel about it.
I have one question always on the thermal storage around the configuration. Do you also have the integrated steam generator inside the...
No, the steam generator is outside. No, it's outside. It's in a separate system
so
outside.
you're using also.
This is another story, another big.
Yeah, we're gonna talk about this storage concept next week, because it's part of my presentation. This thermocline concept is deployed in an air. We have, I think, really saying the same storage tank. It was built based on
based on your designs, yes. Yeah.
So I think it's also exactly the same size, more or less.
Mm-hmm.
And we tested an integrated steam generator, which is immersed within the thermal storage tank, and it's used to produce steam out of the temperature difference between the two, the upper and bottom layer of the tank. So we're going to discuss about this concept. And yeah, I agree that it is troublesome to start it up for the first time.
Yeah.
Just like any experimental installation, I would say, in general, but under the operational point of view, it works.
It works, yes, that's what I know it works. It's the thermocouples, and I remember the word, the thermocouples that we had problems with. So, yeah, the pump was also an issue because the pump has to be very specific because it runs in using molten salts and at high temperature. It's not a conventional one. So the manufacturer was actually delayed for about a year to send it into us. So, all sorts of... but these are things to be expected when you're doing an experimental facility like that, where most of the components are not off the shelf, but they're custom. So you're sending the design to somebody you want them to have them built under your specifications, and it's a one-off piece. So if something goes wrong, you have to see how you deal with it. Either you adapt your own system to fit the new component, or you have to ask for a new one. And there's our delays, communication issues with the suppliers. And that's how it is. We kind of operate a bit like an engineering unit. We're kind of an R&D department of engineering firm where you develop a technology and you don't really have any components which are off the shelf that you can use, but you have to develop them on your own. But that's the way it is. That's the way it goes. Research is slow and cumbersome sometimes. It doesn't come like that. Yeah.
Maybe it was on the slide that maybe pay attention. What was like the cost of building the tower, prototype tower?
The cost. I have actually quite an analytical breakdown of the costs. I'm trying to remember now on the top of my head. These are off-the-record numbers I'm going to tell you now because they don't correspond, obviously, to an upscale system. But the heliostat field, it was about between 500 and 600 euros per square meter, which is far higher than what you would get in a large-scale commercial facility. So out of that, I think that the tower structure itself, without the receiver and the storage tank, wasn't very expensive. It was about 20,000 euros, something like that. I mean, compared to the rest of the costs, was minuscule. The most expensive thing was the heliostats, by far. Then it was the receiver and the storage tank, and everything else was much less. The whole thing, it was financed by various sources. So it started from an Interreg project. Interreg projects are cooperation projects financed by the European Union between two countries. So we started that with an Interreg project between Greece and Cyprus. Also, NEA had a small part in it, in the first initial designs, mostly about the storage. But then these funds were not enough to finish it off, so we used some of our core funding of the institute that went to the facilities. I think overall it's in the ballpark of about 3 million euros, somewhere there for the whole thing. Which, if you divide the amount of how big thermally the system is compared to how much it cost, it makes no commercial sense whatsoever. But that's not the point. That was never the point anyway.
I was just wondering if you made the heliostats here, or if you made the heliostats.
No, the mirrors themselves were flown over from Australia.
Oh, the CSIRO version.
Yes, the CSIRO version. Yes, the mounting structures and the assembly happened here. It took place in Cyprus, but and there was also issues with that because I think the second or the third batch of mirrors that were flown over got smashed in the Cyprus airport. Some of the operators over the crane or whatever they were using to lift them up in the airport actually let them go from a pretty high, from a height which more than they should, and some of them got smashed. And we had to actually wait for another shipment, so that was another delay. Yeah, these things happen. But the truth is that even though the mirrors were shipped from Australia, this is not something that the local industry cannot do. It's not rocket science. As we talked about on Monday, this is something that the Spanish have done well, and they have actually developed a local industry to produce mirrors, not just for heliostats, but for curved mirrors as well. The Cypriots here have lots of experience in installing solar heat systems for hot water purposes. Obviously, this is not the same engineering challenge. but the workshops are there, and there are many engineers working on it. It will require them quite a big step to go up, but the foundations are here, and I think that this is an industry, if it's sustainable and if it can be sustained for Cyprus and for the region, it's something that countries like Cyprus can do. Or not just for here, but the countries around. Generally, for the MENA belt and Northern Africa, it isn't engineering so challenging.